How are you guys doing, by the way, with the assignment? Are most of you finished? Anyone finished? Put up your hands. Okay, good. So we're doing decent. Okay, good. I'll be holding makeup office hours right after this class. Assignment 2 will be released tomorrow or the day after tomorrow. We haven't fully finalized the date. We're still working on it, and we're changing it from last year. And so we're in process of developing it, and we hope to have it as soon as possible. It's meaty, but educational. You do want to get started on it ASAP once it's released. We might be adjusting the due date for assignment 2 because it is slightly larger, and so we'll be shuffling some of these things around, and also the grading scheme. All of this stuff is kind of just tentative and subject to change because we're still trying to figure out the course. It's still relatively new, and a lot of it is changing. So those are just some heads-up items before we start. Now, in terms of your project proposal, by the way, which is due in roughly 10 days, I wanted to just bring up a few points because you'll be thinking about your project, and some of you might have some misconceptions about what makes a good or bad project. So just to point out a few of them, the most common one probably is that people are hesitant to work with data sets that are small because they think that COMNETs require a huge amount of data to train. And this is true. There's hundreds of millions of parameters in a COMNET, and they need training. But actually, for your purposes in the project, this is kind of a myth. This is not something you have to worry about a lot. You can work with smaller data sets, and it's OK. The reason it's OK is that we have this process that we'll go into in much more detail later in the class called fine-tuning. And the thing is that in practice, you rarely ever train these giant convolutional networks from scratch. You almost always do this pre-training and fine-tuning process. So the way this will look like is you almost always take a convolutional network, you train it on some large data set of, say, images, like, say, on ImageNet, huge amount of data. And then you're interested in some other data set right there. And you can't train your COMNET on your small data set, so we'll train it here, and then we'll transfer it over there. And the way this transfer works is, so here's a schematic of a convolutional neural network. We start with the image on top, and we'll go through a series of layers down to a classifier. So you're used to this, but we haven't, of course, talked about the specific layers here. But we take that ImageNet pre-trained network, we train it on ImageNet, and then we chop off the top layer, the classifier. We chop that off, take it away, and we train the entire convolutional network as a fixed feature extractor. And so you can put that feature extractor on top of your new data set, and you're just going to swap in a different layer that performs the classification on top. And so depending on how much data you have, you're only going to train the last layer of your convolutional network, or you can do fine-tuning, where you actually backpropagate through some portions of the COMNET. And if you have more data, you're going to do backpropagation deeper through the network. And in particular, this pre-training step on ImageNet, people do this for you. So there's a huge amount of people who've trained convolutional networks over long periods of time, weeks, on different data sets. And then they upload the weights of the COMNET online. And so there's something called a Café Model Zoo, for example. And these are all these convolutional networks that have been pre-trained on large data sets. They already have lots of the parameters learned. And so you just take this around and you swap in your data set and you fine-tune through the network. So basically, if you don't have a lot of data, that's OK. And you just take a pre-trained COMNET and you just fine-tune it. And so don't be afraid to work with smaller data set. It's going to work out. OK. The second thing that we saw some problems with last time is that people think they have infinite compute. And this is also a myth I'd just like to point out. Don't be overly ambitious in what you propose. These things take a while to train. You don't have too many GPUs. You're going to have to do hyperparameter optimization. There's a few things you have to worry about here. So we had some projects last year where people proposed projects of training on very large data sets, and you just won't have the time. So be mindful of that. And you'll get a better sense as we go through the class on what is or is not possible given your compute constraints. OK. So we're going to dive into lectures. Are there any administrative things that I maybe left out that you'd like to ask about? OK, good. So we're going to dive into the material. We have quite a bit of it today. So just as a reminder, we're working in this framework of many-batch stochastic gradient descent for training of neural networks. And basically, it's a 4-step process. Training a neural network is as simple as 1, 2, 3, 4. You sample your data. So a batch of your data from a data set, you forward it through your network to compute the loss. You backpropagate to compute your gradients. And then you do a parameter update, where you tweak your weights slightly in the direction of the gradient. And so when you end up repeating this process, then really what this comes down to is an optimization problem, where in the weight space, we're converging into areas of the weight space where you have low loss. And that means you're correctly classifying your training set. And we saw that these neural networks can get very large. And I flashed this image of a neural Turing machine. Basically, these are huge computational graphs, and we need to do backpropagation through them. And so we talked about intuitions of backpropagation and the fact that it's really just a recursive application of chain rule from the back of the circuit to the front. where we're chaining gradients through all the local operations. We looked at some implementations of this, concretely with the forward-backward API on both a computational graph and also in terms of its nodes, which also implement the same API and do forward propagation and backward propagation. We looked at specific examples in Torch and Café, and I drew this analogy that these are kind of like your Lego blocks. These layers or gates are your Lego blocks from which you build out the entire convolutional networks. Then we talked about neural networks, first without the brain stuff, and basically what that amounts to is we're making this F, which goes from your image to class scores, more complex. And then we looked at neural networks from the brain stuff perspective, where this is a crude analogy of a neuron, and what we're doing is we're stacking these neurons in layers. Okay, so that's roughly what we're doing right now, and we're going to talk in this class about this process of training neural networks effectively. Okay, so we're going to go into that. Before I dive into the details of it, I just wanted to kind of pull out and give you a zoomed out view of a bit of a history of how this field evolved over time. So if you try to find where this field really comes from, when were the first neural networks proposed and so on, you probably will go back to roughly 1960, where Frank Rosenblatt in 1957 was playing around with something called perceptron. And the perceptron, basically, it ended up being this implementation in hardware. So they had to, like, they didn't just write code, right? They actually had to build these things out from circuits and electronics in these times, for the most part. And so basically, the perceptron roughly was this function here. And it looks very similar to what we're familiar with. It's just a wx plus b. But then the activation function, which we're used to as a sigmoid, that activation function was actually a step function. It was either 1 or 0. It was a binary step function. And so since this is a binary step function, you'll notice that this is non-differentiable operation. So they were not able to backpropagate through this. In fact, the concept of backpropagation for training neural networks had to come much later. And so they came up with these binary stepwise functions, perceptron, and they came up with these learning rules. And so this is kind of an ad hoc specified learning rule that tweaked the weights to make the desired outcome from the perceptron match the true desired values. But there was no concept of a loss function. There was no concept of backpropagation. It's these ad hoc rules, which when you look at them, they kind of almost do backprop, but it's kind of funny because of the step function, which is non-differentiable. And then people started to stack these. So in roughly 1960, with the advent of Adeline and Madeline by Woodrow and Huff, they started to take these perceptron-like things and stack them into the first multi-layer perceptron networks. And this was still all done in this electronics analogy and actually building it out from hardware. And but still, there's no backpropagation at this time. This was all these rules that they've come up with in terms of like thinking about trying to flip bits and seeing if it works better or not. And it was kind of there was no view of backpropagation at this time. And so roughly in 1960, people got very excited in building out these circuits, and they thought that, you know, this could go really far. We can have these circuits that learn. You have to remember that back then, the concept of programming was very explicit. You write a series of instructions for a computer. And this is the first time that people are thinking about this kind of data-driven approach where you have some kind of a circuit that can learn. And so this was, at the time, a huge conceptual leap that people were very excited about. Unfortunately, these networks would not actually end up working very well right away. So in terms of 1960, for example, they got slightly overexcited and overpromised, and then slightly underdelivered. And so throughout the period of 1970s, actually, the field of neural networks was very quiet, and not much research has been done. The next boost actually came about roughly in 1986. And in 1986, there was this influential paper that basically is the first time that you see backpropagation-like rules in a nicely presented format. And so this is Rumelhart, Hinton, and Wilson. And they were playing with multi-layer perceptrons. And this is the first time when you go to the paper where you actually see something that looks like backpropagation. And so at this point, they already discarded this idea of ad hoc rules. And they formulated the loss function and talked about backpropagation and gradient descent and so on. And so at this time, people got excited again in 1986 because they felt that they now had a principled, nice credit assignment kind of scheme by backpropagation, and they could train multi-layer networks. The problem, unfortunately, was that when they tried to scale up these networks to make them deeper or larger, they didn't work very well compared to some of the other things that might be in your machine learning toolkits. And so they just did not give very good results at this time. And training would get stuck, and backpropagation was basically not working very well, especially if you wanted to have large, deep networks. And this was the case for actually roughly 20 years, where again there was less research on neural networks because somehow it wasn't working very well enough, and you couldn't train deep nets. And in 2006, the research was again reinvigorated with a paper in Science by Hinton and Russ Selekhutinov. I can't say his name, sorry. But basically what they found here was, this was roughly the first time where you can actually have, like, say, a 10-layer neural network that trains properly. And what they did was, instead of training all the layers, like 10 layers, by backpropagation at a single pass, they came up with this unsupervised pre-training scheme using what's called restricted Boltzmann machine. And so what this amounts to is you train your first layer using an unsupervised objective, and then you train your second layer on top of it, and then third and fourth, and so on. And then once all of these are trained, then you put them all together, and then you start backpropagation. Then you start the fine-tuning step. So it was a two-step process of first we do this pre-training stepwise through the layers, and then we plug them in, and then backpropagation works. And so this was the first time where backpropagation, it needed basically this initialization from the unsupervised pre-training, otherwise it would not work out of, like, from scratch. And we're going to see why in this lecture. It's kind of tricky to get these deep networks to train from scratch using just backprop, and you have to really think about it. And so it turned out later that you actually don't need this unsupervised process. You can just train with backprop right away, but you have to be very careful with initialization. And they used sigmoid networks at this point, and sigmoids are just not a great activation function to use. And so basically, backprop works, but you have to be careful in how you use it. And so this was in 2006, so a bit more researchers kind of came back to the area, and it was rebranded as deep learning, but really it's still neural networks, synonymous, but it's a better word for PR. And so basically at this point, things started to work relatively well, and people could actually train these deeper networks. Now, still not too many people paid attention, and when people started to really pay attention was roughly, I think, around 2010 and 2012. So specifically in 2010, there were the first really big results where neural networks really worked really well compared to everything else that you had in your machine learning toolkit, like, say, kernels or SVMs and so on. And this was specifically in the speech recognition area, where they took this GMM-HMM framework, and they swapped out one part and subbed in a neural network. And that neural network gave them huge improvements in 2010, and this was work done in Microsoft. And so people started to pay attention because this was the first time neural networks really gave large improvements. And then we saw that again in 2012, where it played out even more dramatically in the domain of visual recognition in computer vision, where basically we took this 2012 network by Alex Kruchevsky, Ilya Sutskever, and Jeff Hinton, and basically it crushed all the competition from all the features, and there was a really large improvement from these neural networks that we witnessed, and that's when people really started to pay attention, and that's since then the field has kind of exploded, and there's a lot of area done in this field now. And so we'll go into details, I think, a bit later in the class on why it started to work really in 2010. It's a combination of things, but I think we figured out better ways of initializing, of getting these things to work, of activation functions, and we had GPUs and we had much more data. And so really a lot of the stuff before didn't quite work because it was just not there in terms of compute data, and some of the ideas just needed tweaking. Okay, and so that's rough historical setting. So we basically went through overpromising, underdelivering, overpromising, underdelivering, and now it seems like things are actually starting to work really well, and so that's where we are at this point. Okay. So I'm going to now dive into the specifics, and we'll actually dive into neural networks and how you train them properly. So the overview of what we're going to cover over the course of the next two lectures is a whole bunch of independent things. So I'll just be kind of peppering you with all these little areas that we have to understand and see what people do in each case. And we'll go through them, the pros and cons of all choices, how you actually properly train these neural networks in real-world data sets. So the first thing we're going to talk about is activation functions, as I promised, I think, a lecture or so ago. So activation function is this function f at the top of a neuron. And we saw that it can have many different forms. So sigmoid, 10H, ReLU, these are all different proposals for what these activation functions can look like. And we're going to go through some pros and cons in how you think about what are good desirable properties of an activation function. So historically, the one that has been used the most is the sigmoid nonlinearity, which looks like this. So it's basically a squashing function. It takes a real valued number, squashes it to be between 0 and 1. And so the first problem with the sigmoid is that, as was pointed out a few lectures ago, there's a problem that saturated neurons, which are neurons that output either very close to 0 or very close to 1, those neurons kill gradients during backpropagation. And so I'd like to expand on this and show you exactly what this means. And this contributes to something that we'll go into called the vanishing gradient problem. So let's look at a sigmoid gate in the circuit. It receives some value x, and sigma of x comes out. And then in backprop, we have dl by d sigma. And we'd like to backprop it through the sigmoid gate using chain rule so that we have dl by dx at the end. And you can see that through chain rule basically tells us to multiply those two quantities. And so think about what happens when this sigmoid gate receives input of either -10 or 0 or 10. It computes some value, and then it's getting some gradient from the top. And what happens to that gradient as you backprop through the circuit in any of these cases? What is the possible problem in some of these cases?
The gradient is really low when x is -10 or 10.
So, okay. So you're saying that the gradient is very low when x is -10 or 10. And the way to see this is basically, we have this local gradient here that will be multiplying with this gradient. This local gradient, d sigma by dx. When you're at -10, you can see that the gradient is basically 0, because the slope at this point is 0. And the gradient at 10 will also be near 0. And so the issue is that your gradient will drop in from here, but if your neuron is saturated, so it basically either outputted 0 or outputted 1, then the gradient will be killed. It will just be multiplied by a very tiny number, and gradient flow will stop through the sigmoid neuron. So you can imagine if you have a large network of sigmoid neurons, and many of them are in a saturated regime where they're either 0 or 1, then gradients can't backpropagate through the network because they'll be stopped if your sigmoid neurons are in these saturated regimes. The gradients only flow if you're kind of in a safer zone in what we call an active region of a sigmoid. And so that's kind of a problem. We'll see a bit more about this soon. Another problem with sigmoids is that their outputs are not zero-centered. So we'll talk about data preprocessing soon, but you always want to, when you preprocess your data, you want to make sure that it's zero-centered, right? And in this case, suppose you have a big network of several layers of sigmoid neurons. They're outputting these non-zero-centered values between 0 and 1, and we're putting more basically linear classifiers that we're stacking on top of each other. And the problem roughly with non-zero-centered outputs, I'll just try to give you a bit of an intuition on what goes wrong. So consider a neuron that computes this function, right? So it's a sigmoid neuron looking at, it's just computing wx plus b. And what can we say about, think about what you can say about the gradients on w during backpropagation if your x's are all positive, in this case between 0 and 1. So maybe you're a neuron somewhere deep in the network. What can you say about the weights if all the x's are positive numbers? They're kind of constrained in a way. Go ahead.
All the elements of the gradients of W is positive or negative?
Right, so what you said is all the gradients of W are either all positive or all negative. And that is because gradient flows in from the top. And if you think about the expression for all the W gradients, they're basically x times the gradient on f. And so if the gradient on the output of the neuron is positive, then all your W gradients will be positive and vice versa. So basically, you end up with this case where, suppose you have just two weights. So you have the first weight and the second weight. What ends up happening is either all your gradient for that as this input goes through and you compute your gradient in the weights, they're either all positive or they're all negative. And so the issue is that you're constrained in the kind of update you can make, and you end up with this undesirable zigzagging path if you want to get to some parts that are outside of these regions. So this is kind of like a slightly hand-wavy reason here. But just to give you intuition, and you can see this empirically, when you train with things that are not zero-centered, you'll observe slower convergence. And this is a bit of a hand-wavy reason for why that might happen. But I think if you actually wanted to go much deeper into it, you can, and there are papers written about this. But you have to then reason about mathematics of Fisher matrices and natural gradients, and it gets a bit more complex than this. But I just wanted to give you intuition for, you want to have zero-centered things in the input, you want to have zero-centered things throughout, otherwise things don't converge as nicely. And so that is a downside of a sigmoid neuron. And the last one is that exp function inside this expression is kind of expensive to compute compared to some of the alternatives of other nonlinearities. And so it's just a small detail, I suppose. When you actually train these large convolutional networks, most of the compute time is in convolutions and these dot products, it's not in this exp operation. And so it's kind of vanishingly small contribution, but it's still something that is a bit of a downside compared to the other parts. So I'll go into 10H, and I'll take a few questions then. So 10H is an attempt to fix one of these problems, in particular the fact that it's non-zero centered sigmoid. So Jan LeCun in 1991 wrote a very nice paper on how you optimize neural networks, and I've linked to it from the syllabus. And he recommended that people use 10H of X instead of sigmoid. And 10H of X basically is kind of like two sigmoids put together. You end up with being between -1 and 1, and so your outputs are zero-centered. But otherwise, you have still some of the other problems. Like, for example, you have these regions where if your neurons get saturated, no gradients flow, and so we haven't really fixed that at this point. But so 10H is, I think, strictly preferred to sigmoid because it has all the same problems except for one. Okay. I'll continue, and then maybe we can take more questions. So around 2012, in a paper by Alex Kruchevsky, this is the first convolutional networks paper, they proposed that actually they noticed that this nonlinearity where you use max of 0 and x instead of sigmoid or 10H just makes your networks converge much quicker. And in their experiments, almost by a factor of 6. And so we can go back and try to think about why is this. And we're kind of reading into it. Like, you can see that it works better in practice, but explaining it is not always as easy. So here's some hand-wavy reasons, I think, for why people are thinking that this works much better. So one thing is that this ReLU neuron, it does not saturate, at least in the positive region. So at least in this region, you don't have this vanishing gradient problem where your gradients will just kind of die. And you have this issue where the neurons are only active in a small area that is bounded from both sides. But these neurons are actually active in a sense that they backpropagate correctly, or not correctly, but at least they don't not backpropagate all zeros, at least in half of their regions. They're much more computationally efficient because you're just doing thresholding. And experimentally, you can see that this converges much, much faster. So this is called the ReLU neuron, or the rectified linear unit, and it was pointed out in this paper for the first time that this works much better. And this is kind of like the default recommendation of what you should use at this point. At the same time, there are several problems with this ReLU neuron. So one thing, again, notice that it's not zero-centered outputs, so not completely ideal, perhaps. And a slight annoyance of the ReLU neuron that we can talk about and think about is what happens when this ReLU neuron outputs a 0. What happens during backpropagation if a ReLU neuron does not become active? So in the forward pass, a ReLU neuron stays inactive. Then during backprop, what does it do?
Kills the gradient.
It kills the gradient. And so the way to see this, of course, is that we have the same picture. And if you're at negative, say, 10, then your local gradient here will just be 0 because there's just 0 gradient identically. It's not just you squish the gradient down, you actually kill it completely. So any neuron that does not activate will not backpropagate downwards. Its weights will not be updated, and nothing happens below it, at least for its contribution. And at x equals 10, what is the local gradient?
1.
It's just 1. So a ReLU neuron just passes through a gradient. It's just a gate. If during the forward pass its output was positive, then it just passes gradient through. Otherwise, it kills it. It's kind of like a gradient gate. And by the way, what happens when x is 0? What is your gradient at that point?
Questionable.
Undefined.
It's actually undefined. That's right. The gradient does not exist at that point. We only talk about, whenever I talk about gradient, just assume that I always mean subgradient, which is a generalization of gradients to functions that are sometimes non-differentiable. So here the limit does not exist, but there's a whole bunch of subgradients that could be 0 or 1. And so that's what we use usually. In practice, this distinction doesn't really matter too much. But I wanted to also point this out in the case of the binary max gate, max of x and y, and someone asked the question, what happens if x and y are equal? Then in that case, you kind of also have a kink in the function and makes it non-differentiable. But in practice, these things don't really matter. Just pick one. So you can have a gradient of 0 or 1 there, and things will work just fine. And that's roughly because these are very unlikely cases that you end up right there. OK, so the issue with ReLU, roughly, here's the problem that happens. In practice, you try to use ReLU units. And one thing that you have to be aware of is you have these neurons that if they don't output anything, they won't get any gradient. They'll kill it, and they won't update. And so let's see. So the issue is, suppose you have a sometimes what can happen is when you initialize your ReLU neurons, you can initialize them in a not very lucky way. And what ends up happening is, suppose this is your data cloud of inputs to your ReLU neurons. What you can end up with is what we call a dead ReLU neuron. So if this neuron only activates in a region outside of your data cloud, then this dead ReLU will never become activated, and then it will never update. And so this can happen in one of two ways. Either during initialization you were really, really unlucky and you happened to sample weights for the ReLU neuron in such a way that that neuron will never turn on. In that case, the neuron will not train. But more often what happens is during training, if your learning rate is high, then think about these neurons as kind of like jittering around. And what can happen sometimes by chance is they just get knocked off the data manifold. And when that happens, then they will never get activated again, and they will not come back to the data manifold. And you can see this actually in practice. Like sometimes you can train a big neural net with ReLU units, and you train it, and it seems to work fine. And then what you do, you stop the training, and you pass your entire training data set through your network, and you look at the statistics of every single neuron. And what can happen is that as much as like 10 or 20% of your network is dead. These are neurons that never turned on for anything in the training data. And this can actually happen. Usually it's because your learning rate was high, and so those are just like dead parts of your network. And you can come up with hacky schemes for reinitializing these things and so on. People don't usually do it as much. But that's something to be aware of, and it's a problem with this nonlinearity. And so especially for initialization, because of this dead ReLU problem, what people like to do is normally you initialize the biases with 0. Instead, people initialize with slightly positive numbers, like say 0.01, because that makes it more likely that at initialization, these ReLU neurons will output positive numbers and they'll get updates. So it makes it less likely that a neuron will just never become activated ever throughout training. But I think this is slightly of a controversial point. I've seen people claim that it helps. I've seen some people say that it actually doesn't help at all. And so just something to think about. OK, any questions at this point? We had sigmoid, 10H, and ReLU. I'm going to go into some other ones. OK, good. So let's look at things like people trying to fix ReLUs. So one issue with ReLUs is these dead neurons are not ideal. So here's one proposal, which is called the leaky ReLU. And the idea with leaky ReLU is basically we want this kink, and we want this piecewise linearity, and we want this efficiency of ReLU. But the issue is that in this region, your gradients die. So instead, let's make this slightly negatively sloped here, or slightly positively sloped, I suppose, in this region. And so you end up with this function, and that's called a leaky ReLU. And so some people, there are papers showing that this works slightly better. You don't have this issue of neurons dying. But I think it's not completely established that this works always better. And then some people play with this even more. So right now this is 0.01, but that can actually be an arbitrary parameter. And then you get something that's called a parametric rectifier, or p-ReLU. And basically the idea here is you introduce, this is 0.01. That can be an arbitrary alpha, which is a parameter in your network. And this alpha can be learned. You can backpropagate into it. And so these neurons basically can choose what slope to have in this negative region. OK? And so they can become a ReLU if they want to, or they can become a leaky ReLU, or they have the choice, roughly, for every neuron. And so this is the kinds of things that people play with when they try to design better nonlinearities. Go ahead.
So you're saying that alpha can be set by neurons above stream?
So alpha here would be a parameter that you backpropagate to in just a very normal way. Okay. In your computational graph, every neuron will have its alpha, just like it has its own bias. OK, go ahead.
Is there some restriction on being an activation function? Can alpha be 1?
Yeah, I'm not sure if they worry about this a lot. So if alpha is 1, then you're going to get an identity. So that's probably not something that backpropagation will want, in the sense that if that was an identity, then that shouldn't be very computationally useful. So you might expect that maybe backpropagation should not actually get you to those regions of the space, hand-wavy reason, perhaps. I don't actually think, if I remember correctly, there's no specific things where people really worry about that too much. But I could be wrong. I read the paper a while ago now, and I don't use these too much in my own work. OK? And then, so one issue still is, as we saw, so these are different schemes for fixing the dead ReLU neurons. There's another paper that only came out, for example, roughly 2 months ago. So this just gives you a sense of how new this field is. There are papers coming out just 2 months ago trying to propose new activation functions. One of them is exponential linear units, or ELU. So just to give you an idea about what people play with. it tries to have all the benefits of ReLU, but it tries to get rid of this downside of being non-zero centered. And so what they end up with is this blue function here that looks like a ReLU, but in the negative region, it doesn't just go to 0, or it doesn't just go down as a leaky ReLU, but it has this funny shape. And there are 2 pages of math in that paper justifying partly why you want that. And roughly when you do this, then you end up with 0 mean outputs. And they claim that this trains better. And I think there's some controversy about this. And so we're basically trying to figure all of this out, active area of research. And we're not sure what to do yet. But ReLUs right now are like a safe recommendation if you're careful with it. OK, so that's ELUs. And one more I would like to mention, because it's relatively common, and you'll see it if you read about neural networks, is this max-out neuron from Ian Goodfellow et al. And basically, it's a very different form of a neuron. It's not just an activation function that looks different. It actually changes what a neuron computes or how it computes. So it doesn't just have this form of f of w transpose x. It actually has 2 weights. And then it computes max of w transpose x plus b and another set of w transpose x plus b. So you end up with these like 2 hyperplanes that you take a max over, and that's what the neuron computes. So you can see that there are many ways of playing with these activation functions. So this doesn't have some of the downsides of a ReLU. This won't die. And it's still piecewise linear. It's still efficient. But now every single neuron has 2 weights. And so you've kind of doubled the number of parameters per neuron. And so maybe that's not as ideal. So some people use this, but I think it's not super common. I would say that ReLUs are still most common. Go ahead.
So because the loss functions will be different when they use different activation functions, the weights which you obtain might not be the same, right? Even if, I mean, they might have different convergence rates, but they also can result in different weights at the end of the simulation.
That's right. So what is your question? Sorry.
So because the loss functions themselves are different when you use different activation functions. So the weights also will be different in both if you use different activation functions. Right?
That's right. So the weights will end up, based on what the activation functions are, the dynamics of the backprop into those weights will be different. And so you end up with different weights, for sure.
So isn't the argument more like which loss function is like closer to the reality? As in, which loss function is better in some sense, rather than? Yeah,
I think it's complicated. The reason it's complicated is a lot of the optimization process is not just about the loss function, but just like about the dynamics of the backward flow of gradients. And we'll see a bit about that in the next few slides. You have to really think about it dynamically more than just loss landscape and how it's a complex. And also we use specifically stochastic gradient descent, and it has a particular form. And some things play nicer, some nonlinearities play nicer with the fact, like the optimization is tied, the update is tied into all of this as well. And it's kind of all interacting together. And the choice of these activation functions and the choice of your updates are kind of coupled. And it's kind of very unclear when you actually optimize this. It's kind of a complex thing. Okay. So TLDR here is that use ReLU. You can try out these guys. You can try out 10H, but you shouldn't expect too much. I don't think people use it too much right now. And don't use sigmoid, because basically 10H is strictly better. And you won't see people use sigmoid now anymore. Of course, we use it in things like long short-term memory units, LSTMs, and so on. And we'll go into that in a bit in recurrent neural networks. But there are specific reasons why we use them there, and that we'll see later in the class. And they're used differently than what we have covered so far in like this just fully connected sandwich of matrix multiply, nonlinearity, and so on, just having a basic neural network. Okay, so that's everything I wanted to say about activation functions. It's basically this one hyperparameter in our functions that we worry about. There's research about it, and we haven't fully figured it out. And there's some pros and cons, and many of them come down to thinking about how the gradient flows through your network, and these issues like dead ReLUs. And you have to really know about the gradient flow if you try to debug your networks and to understand what's going on. Okay. So let's look at data preprocessing very briefly. How many time? Okay. So data preprocessing, just very briefly. Normally, suppose you just have a cloud of original data in 2 dimensions here. Very common to zero center your data. So that just means that along every single feature, we subtract the mean. People sometimes also, when you go through machine learning literature, try to normalize the data. So in every single dimension, you normalize, say, by standard deviation, called standardizing. Or you can make sure that the min and the max are within, say, -1 or 1, and so on. There are several schemes for doing so. In images, it's not as common, because you don't have separate different features that could be at different units. Everything is just pixels, and they're all bounded between 0 and 255. So it's not as common to normalize the data, but it's very common to zero center your data. You can go further. Normally in machine learning, you can go ahead and your data has some covariance structure by default. You can go ahead and make that covariance structure be diagonal, say, for example, by applying PCA. Or you can go even further and you can whiten your data. And what that means is you kind of even squish, after you performed PCA, you also squish your data so that your covariance matrix becomes just a diagonal. And so that's another form of preprocessing you might see people talk about. And these are both, I go much more detail in the class notes on these. I don't want to go into too many details on them because it turns out that in images, we don't actually end up using these, even though they're common in machine learning. So in images, specifically, what's common is just the mean centering, and then a particular variant of mean centering that is slightly more convenient in practice. So in mean centering, we say have 32 by 32 by 3 images of CFAR. If you want to center your data, then for every single pixel, you compute its mean value over the training set, and you subtract that out. So what you end up with is this mean image that has basically a dimension of 32 by 32 by 3. So I think the mean image, for example, for ImageNet is just this orange blob. So you end up subtracting that from every single image to center your data to have better training dynamics. And one other form that is slightly more convenient is subtracting just the per channel mean. So you go in red, green, and blue channel, and you compute the mean across all of space. So you just end up with basically 3 numbers of the means in red, green, and blue channel, and you just subtract those out. And so some networks use that instead. So those are the 2 common schemes. This one is slightly more convenient because you only have to worry about those 3 numbers. You don't have to worry about a giant array of mean image that you have to ship around everywhere when you're actually coding this up. OK? So not too much more I want to say about this. Just basically subtract the mean in computer vision applications. Things don't get much more complex than that. In particular, doing PCA and so on, this used to be slightly common. The issue is you can't apply it on full images because your images are very high-dimensional objects with lots of pixels. And so these covariance matrices would be huge. And people try to do things like only doing whitening locally. So you would slide a whitening filter through your images spatially. And that used to be done several years ago, but it's not as common now. It doesn't seem to matter too much. OK, good. So we'll dive into weight initialization. Very, very important topic. One of the reasons that I think early neural networks didn't quite work as well is because people are just not careful enough with this. So one of the first things we can look at is, first of all, how not to do weight initialization. So in particular, you might be tempted to just say, OK, let's start off at all the weights are equal to 0. And you use that in your neural network. So suppose you have like a 10-layer neural network, and you set all the weights to 0. Why doesn't that work? Why isn't that a good idea?
All data will output the same.
Sorry, go ahead.
All output will just all output 0.
Yeah, so basically just all your neurons output the same thing. In backprop, they will behave the same way. And so there's nothing, as we like to call it, symmetry breaking. So all the neurons are computing the same stuff. And so in backprop, they will all look the same. They'll compute the same gradients and so on. So not the best thing. So instead, people use small numbers, small random numbers. So one way you can do that, for example, that is a relatively common thing to do, is you sample from a unit Gaussian with a 0.01 standard deviation. So small random numbers. So that's your W matrix, how you would initialize it. Now, the issue with this initialization is that it works OK, but you'll find that it only works OK if you have small networks. But as you start to go deeper and deeper with neural networks, you have to be much more careful about initialization. And I'd like to go into exactly what breaks and how it breaks and why it breaks when you try to do these naive initialization strategies and you try to have deep networks. So let's look at what goes wrong. So what I've written here is a small IPython notebook. So what we're doing here is, I'm going to step through this just briefly. I'm sampling a data set of 1,000 points that are 500 dimensional. And then I'm creating a whole bunch of hidden layers and nonlinearities. So say right now we have 10 layers of 500 units, and we're using 10H. And then what I'm doing here is I'm just basically taking unit Gaussian data, and I'm forwarding it through the network. And with this particular initialization strategy, where right now that initialization strategy is what I described in the previous slide. So you sample from unit Gaussian, and you scale it by 0.01. So what I'm doing here in this for loop is I'm forward propagating this network, which is right now made up of just a series of layers of the same size. So we have 10 layers of 500 neurons on each layer. And I'm forward propagating with this initialization strategy for a unit Gaussian data. And what I want to look at is what happens to the statistics of the hidden, of the neurons activations throughout the network with this initialization. So we're going to look specifically at the mean and the standard deviation, and we're going to plot the mean standard deviation, and we're going to plot the histograms. So we take all this data through, and then say at the 5th layer, we're going to look at what values the neurons take on in, say, the 5th or 6th or 7th layer, and we're going to make histograms of those. So with this initialization, if you run this experiment, it ends up looking as follows.